So now I first want to sort of take a look at these matrices in terms of solving these systems of equations, because that was sort of the first inspiration for these collection of numbers. So consider this system right here. Here we have x plus y equals 5 and x minus y equals minus 1. Now certainly there are a variety of ways of solving this simple system. You could use the elimination method, you can substitute, and so forth. But now I want to try to use this simple example as a template to the idea of using this matrices technique. And in fact, this technique for solving this system is called the Gauss-Jordan method. The Gauss-Jordan method. And here's what the method is. The method is, let's just make a pact right now that here will always be x's, and here will always be y's, and here will always be constants. If I make that pact with you, then I can actually forget about those variables and just write this instead of the first equation, because there's a 1 in the x spot, a 1 in the y spot, and a 5 over here. You see how these two things are actually the same? What would I write here? Well, here I'd write a 1 and a minus 1 and a minus 1. So in fact, I can strip away the equal signs and all that other stuff, the x's and the y's, as long as you promise me x's go here and y's go here. OK, now, what can I do? If you think of this now as a matrix, if you think of this now as a collection of just numbers in a grid like this would be a 2 by 3 grid. And it's something that's called an augmented matrix, because I have this little dotted line here to remind me these are variables, x, y, and these are the numbers. But there's a little matrix right there. Now, what things could I do to this that would be legal operations in terms of the legal operations that I could do with these equations? Well, if you just think about what you can do with equations, you can immediately see what those rules should be here in the Gauss-Jordan method. Rule number 1 is I can first of all flip the order of these. Like doing this, it's still the same system. And that would be equivalent to doing this. So flipping a row with another row is no problem, because it's just basically moving around the equations. So that's fine. What else could I do? Well, I can always take an equation and multiply it through by something. It doesn't change the equation. So I can also do that here. I could take any row I want and multiply that row through by a constant. Like I can multiply everything here by 3 if I wanted to. 3, 3, 15. And that would be equivalent to multiplying this equation through by 3. 3x plus 3y equals 15. It doesn't change the equation. So I can actually multiply through by something, as long as I go all the way through. What else do I tend to do with these equations? When I do the substitution, I like to be able to multiply an equation through by something and then add it to another equation. Well, I can do that here too. What would that look like? I could take any row and actually multiply it through by something and add it to another row and replace that other row by that addition. So that would actually be multiplying through by 3 and then adding it to this row and replacing that row by what the answer is. That's basically taking this, multiplying it by 3, and adding it to this equation and putting that equation right there. Doesn't change the value. So in fact, those are the basic rules in the Gauss-Jordan method. You can sort of flip the order of these things. That's not a big deal at all. You can multiply any row through by a constant, and you can replace any row by taking another row, multiplying it through by something, and then adding it or subtracting it to that row. Now, just using those methods, we can actually now solve this system just using this matrix. Now, what's the goal? Well, the goal at the end of the day would be to have a matrix that looks like this. Let me just draw you what the goal would look like. So here's our fantasy. At the end of the day, we want 1, 0, 0, 1, dot, 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 and then some number here and some number here. Let's see why that really is our goal. That's our goal because if we had that, what does that mean? What's the top equation? 1x and no y's equals that. So that means x equals that number. So that means x equals. And what would this mean? No x's and 1 y, so y equals that. So in fact, if I could get this system to be in this form, that would mean that in fact I know what x equals and I know what y equals. I can just read them off the right hand column. So my goal is to take those rules I just told you about, switching rows, subtracting rows and adding them and so forth, and to try to massage this to look like that. And that would actually be solving this equation, the system of equations. So let's actually try to do that right now. So what I do is I'm going to start with this system right here. So I'm going to write that up here. So I have 1, 1, 1, minus 1. And I have 5 and a minus 1. So there's the system. Remember, this is always the x's and these are always the y's. Now if I dispense with this. My goal is to get this to look like this, using those legal operations, which are really just convert down to equations, operations with equations. So the first thing I'll do is I'll actually take this row and add it to that row and put that in this row. So I'm going to replace this row by the sum of this row and that row. Why? Because if I add these two things, that'll put a 0 right there. And that's a good thing. I want a 0 there. So if I do that, what I'm doing here is I'm going to, in this row, I'm going to take row 1 and add row 2. So in place of this, I'm going to put the sum of these two rows. So just add. 1 and 1 is 2. 1 and minus 1 is 0. 5 and minus 1 is 4. And I'll do nothing here. That's the equivalent, basically, of adding the two equations up, and this is what you get. Now, I want a 1 here, so I'll just divide the top thing through by 2, which is a legal move, because that's just taking the equation and dividing it through by 2. So if I do that, I get 1, 0, 2. And I still have this, 1 minus 1 minus 1. But now what could I do? Well, I could take this and subtract this and put that in here. That's just the substitution, which would look like this. What I'm going to do is right here, I'm going to put in, let's see, I'm going to take row 1 and subtract off row 2. So this minus, so let me put this in first of all, and I'm not going to do anything up here. So this minus that is 0. This minus that becomes a 1. This minus that becomes a 3. And look, I got it in my fantasy form. If you remember, this is the x and this is the y. This means x equals 2. So x equals 2, and this means y equals 3. So now if I go back to the original equation, I should have this thing satisfied. If x equals 2 and y equals 3, their sum is 5. And yet, if I take 2 and subtract 3, I get negative 1. This actually works. And notice what I did. I just did all the manipulation involved in looking at the elimination method. But instead of doing it with all the x's and y's there, I just used the coefficients and carefully moved things around by adding rows to other rows and so forth and getting it into this form. This is the Gauss-Jordan method. You want 1s along this diagonal here and 0s everywhere else. So you can just say x equals, y equals. OK. We'll take a look at this method again up next.